this is about now, we talked about two things to remind you. We talked about how to analyze the simple wave beams and slabs, and we talked about how you can analyze the two-way slab. Now we come to the design of floor slab systems that are composed of many components: flat slab, flat plate, drop panel, waffle slab, beam slab, all of those. They are all treated in the same way by the analysis and design method, and we are going to look at the simplified approach first. For the detailed approach, of course, you use finite element. So that is always the case. Flat slab, you know what it is. You know, for our purpose, the slab system supported on columns, flat plate, flat slab, flat and drop panels, waffle slab, web slab, beam slab, beam dash slab, slab with beams, and you know the difference between beam and slab. And this is the limit, that it should be two-way, it should not be one-way, right? So the long to short, the ratio between long and short span and the beam to slab ratios are given here. So the things should be within that. It is not only the ratio between this long and short span, but also it also talks about the beam and slab stiffness ratio, because that is one of the criteria to qualify as beam dash slab. Otherwise, it will become beam comma slab, and then you have to go to the two-way slab design concept that we discussed earlier, right? So you should be very clear how this method is applied. Does not apply to beam and slab, one-way slab, so one-way joist, beam girder, and slab, wall supported slab. So this is not governed by this procedure. Okay? That I already explained most of those things that you can do for the others. Flat slab types. So basically we are talking about these types. These are the pictures taken from which program? Right, so you know already. So this is completely covered in Gear program. So you can go back and try this design by yourself and see how it works. So flat plate with cap, so you know all of these types. These are covered by this design approach. Panel. What's a panel? These are the terminologies. Panel is a portion of the floor bounded by 4 columns, let's say. So it's a panel between, so this in between, so this is the one panel of the slab that is bounded by 4 column center lines or beam center lines. Includes everything within that portion, whether it's a drop panel, it's a beam, it's a column capital, columns, everything within that is included in that panel. And then design strip is a continuous strip along the center line that we will see. And design strip concept is very, very important. The concept of a design strip is critical to the design of slab systems. And I will explain more about it as we go along. Column strip is portion of the design strip on center of the columns. Middle strip is a portion between column strips, and then drop panel is a portion on the column. So you should understand what this means, all of these statements, and we will show them soon. Column capital, attached torsional member, equivalent frame, all of these terms are important when you're designing these slab systems. Design strip concept. Now this is taken from the finite element analysis of a slab that I showed you last time. These are the column locations, and there could be beams here, there may not be beams here. And we are talking about the bending in one direction. Same thing will happen in the other direction. So we are plotting the bend moment intensity in this direction. And we can see that the negative is red, purple is, so this is a negative moment here, this is positive moment here. So moments are going, green is less positive, this is less negative, and something like that. So you can see the pattern. Now what is important or interesting from this is the color bands. Very clearly there is a system going on here. Something is going on very clearly. A certain band of colors here, a certain band here, a certain band of colors here, and a certain here. And same thing will happen in the other direction. So based on this plot, we can divide this slab into portions. One portion which will take these colors, one portion which will take the other colors, greens and reds, or greens and above, and blues, light blues, and that in the other side. And we can divide the lines approximately there, right? So the behavior here is clearly different from behavior there, correct? As the colors show. So we can say, okay, this is column strip and that is middle strip. So the portion which is resting on the columns and some portion around there, certain width, we will call it as a column strip, and the portion between that we will call them as middle strip, right? And half of one middle strip and half of the other middle strip plus the column strip, we will call it as a design strip. So that is like band of slab running along the column, centered on the column is in the middle, half this side, and on that one we have this part of that is middle strip, part of that is middle strip, and then the middle portion of that is actually the column strip. Now the width of these depend on many things. The width of the column strip and width of the middle strips depends on many factors, right? Conceptually, this is like a beam, white beam resting on the column, and this is a slab which is going parallel to that, also deflecting, and in another direction it will be supported on these beams. So when we do that, it will be like this. So it's conceptually, it's similar to that idea. Just the beam is too wide, it includes portion of the slab also. How wide this is depends on the span ratios and also the column spacing. So if this is L1, the span along, let's say we're talking about a design strip like this, and same way we will have design strips the other way. So in a flat slab or slab design system, we do it two times. One time strips running in X direction, and second time strips running in Y direction. You can say easily, well, many buildings are not like this. They have inclined center line. What do you do with that? So we try to, and it's of course it's a problem where you need to create strips along column lines wherever they're going, right? Sometimes they are very random, so it becomes difficult. So practically, it's not all that easy to create such strips always, right? And so we have to be careful and we have to use our judgment to how to do that. And that's another aspect we can talk later. But let's finish the concept first. So concept is that we have span along the strip and we have spans perpendicular to the strip called L2. L1 is always along the strip, L2 is always perpendicular to the strip. So design strip will be like this. Half middle strip, column strip, we define like this. And then we treat this entire design strip as if it was a beam center line. So we analyze this as one very wide beam from here to here. But we will make some changes to account for the column size and the fact that there is no support throughout the width. So we will have to make some changes in our concept. But this is how we look at the design strip. So each design strip is analyzed as a wide beam, so to speak. And it may contain beams, real beams inside, or it may contain beams on the other direction. So if this beam is there, it becomes part of the design strip. If there is a beam here, half of that beam and half of that beam become part of this design strip, and their calculation is also taken into account. Even though they are perpendicular to the direction, their contribution is considered. Right? If there is a drop panel, we also consider that. So everything within that strip becomes part of the design strip and becomes part of the calculation. And this is how the codes, if you look at the other location, you can see sometimes you only have half because there is no slab here on the edge. So you have only the design strip is only this portion, doesn't have anything. So the design strip will be here, column strip will be here. Design strip will have half of the middle strip and half of the column strip in that case. And sometimes it will have both of them. So strips can be interior, exterior, longitudinal direction, transverse direction, and additional strip that may need to be added for diagonal or other places, right? Components, we have talked about, all of these are part of the design strip. So it could be like this. You can see from here, design strips could have interior, equal, unequal, with cantilever, without cantilever. So these are all different types of design strips. Location could be here. From the gear you can see it could be intermediate floor, it could be top floor. So design strip must contain the columns also. Column below and column above. That is part of the design strip because that is falling in the design strip. So it is not only the slab, it's the column below and column above, and the slab and the beam and the top panel and the column capital. Everything in that portion becomes our design strip. So this is how the design strip will look like in the elevations. This is the main step, how you do the design. Select the layout and type of slab system. Select trial thickness for the slab. Select typical strip for design, because there will be hundreds of strips in real building. You cannot design every strip. So you have to say, okay, this strip, these 7 strips look the same. So I will design one of them and apply the same reinforcement 7 times. These 6 look the same. So you have to sit down on the plan and you say, okay, these are the typical strips that I'm going to design. These are the typical floors. Building is 30 floors. You don't need to design slab on all 30 floors. You just pick up typical floors and then design typical strips, right? So you have to be sensible, intelligent about it, otherwise you will spend all your life designing one building. Choose the design method. We have 2 methods. Compute positive, negative moment. Distribute the moment across the width in the strip. Design for bending, design for shear, check for deflection. Very simple, right? The difficult steps are, number 1 important step is trial thickness to start with. Second one is how to calculate the moments, how to distribute the moments, right? These are bit questions, difficult things to do. Not difficult, but something to consider. First of all, we have 2 design methods to do this. One is called direct design and one is called equivalent frame design. So if your project falls in this category, you can use direct design method. Direct design method is, you don't need to do any analysis. You can calculate the bending moment by using WL squared by 8, the formula that I told you. So we can, based on that, we can see if this is at least 3 spans. So if this is satisfied, you can use direct design method. Very easy, very quick. You don't need any computer, you don't need anything. You don't even need gear for that. If not, then you use equivalent frame method for everything else. Remember, finite element analysis is not here because that is not an approximate method. So that is a totally different thing, right? We will talk about that later. Within the approximate methods, there are 2 categories, direct and equivalent. Slab thickness. How do we calculate slab thickness? This is a complicated thing in flat slab system, not as easy as you would imagine. Because slab thickness will control the deflections and vibrations, clear span, panel aspect ratio, relative stiffness, steel yield strength. These are the things that govern the slab thickness related to deflection and vibration. So if you want to control the serviceability of the slab, the thickness will depend upon these parameters. How much deflection is allowed, how much vibration is allowed, what are the aspect ratios of the slab, and what are the steel yield strength. Okay? At the same time, slab thickness is very important for the second part, which is strength, in which the concrete strength is important, Shape and size of column is important. Location of column, interior, exterior corner is important. Presence of opening is important. Amount of direct punching shear, amount of unbalanced moment, and slab thickness. So these things will affect the shear and moment transfer. So the strength part is affected by many parameters, and the deflection part is affected by these parameters. So our slab thickness must satisfy the two important criteria of the deflections and vibrations and of the strength in bending and shear, right? And interestingly, the slab thickness for this one depends on the slab thickness itself. It's not by mistake. So the slab thickness for strength depends on the slab thickness itself, because we will find later that the calculation of the shear parameter depends on the thickness to calculate the thickness. So that's always a problem that we have. Without drop panel, these are very, very approximate limits for deflection control that we can use. And as I mentioned, it does not include the loading in the calculation, which is a drawback. So they are assuming normal loading. So based on this one, you can estimate the starting thickness. The A parameter is the one that depends on the concrete strength, the one that we discussed the last time that we talked about. So this is where A comes in. I asked you this question last time, why the thickness is related to concrete yield strength. You remember? We had a lot of discussion about this one. So these equations are taken from that, AM is taken from these equations. So this factor comes from there, all right? So you can see that this depends on the ratio of the Fy, of the aspect ratio, of the beam parameters, and so on and so forth. So carefully, this formula is quite big, as you can see. Looks complicated, but it's not really that complicated. But it gives you a lot of numbers, so you can check the deflection. But in reality, after all of this, we must still check the deflection calculations. But checking the deflection calculation for a flat slab system is extremely difficult. Very, very difficult to check the deflections of the slab, because it's not a beam that has only one deflection profile. Slab has different deflection along the column, and next to the column, next to the column, next to the column. So there is no single system that you can use. Very difficult, because the strip itself is deforming this way, and it's also deforming the other way. So at the center line, deflection will be different, little bit here, different, and so on. So very, very hard to calculate the deflections of the flat slab system. That is why the codes are giving all these formulas to control that, right? Strength may never be checked. Deflection will almost always be checked in reality. If you make an error in deflection, it will show up. If you make an error in strength calculation, it might not show up, because there is a factor of safety behind that. There is no factor of safety for deflection. So, which means that deflections, if you do not do deflections calculations correctly, it will deflect, and people will see, and it will cause cracking, and it will cause problems. And one important thing sometimes missing here, I think it's not here, the creep factor multiplier, which can be very large, long-term deflection. So you get some deflection today, you say, oh, it looks okay, not so bad. After 5 years, the deflection doubles easily. So then it's no longer good. So we have to make sure that the creep factors are also included in the detailed calculations. So do not compromise on thickness for deflection. One way to overcome the problem is, what is the way to overcome the problem for deflection? What is deflection? You cast something straight, it goes down, right? Why don't we cast it upward so that when it deflects, it becomes straight? So during casting, you provide camber. So when you remove the formwork, after deflection, the slab becomes straight. And then the long-term deflection will start from here, not from the original position. So camber, as simple as that. Design moment. So we said we have two methods of doing that, direct design method and equivalent frame method. Direct design method is compute total panel design moment and knot, assign and knot to supports and midspan, negative and positive. I will show you, don't worry. Distribute moments to various components. Equivalent frame, create equivalent frame, apply loads and analyze the frame, obtain design moments and supports and midspan, distribute moments between components. So what we are saying is that we need to be able to basically calculate how much is the negative moment and how much is the positive moment, and after that we need to calculate how much of that moment goes to middle strip, how much goes to column strip, how much goes to beam, how much goes to column capital, and so on, because there are many components in the slab system. So the first thing is to calculate the moment, total moment. Second thing is to distribute the moment between the various components, right? That's it. So beam, if a beam is very big, it will take more moment than the slab because the distribution will be done based on stiffness. So that means if there's no beam, all the moment will be taken by the slab. If you put a small beam, it will take small moment. If you took a big beam, it will take more beam, more moment. So everything is very fair and systematic. So for the direct design method, the total moment can be calculated as WL squared by 8, as I mentioned, and then out of that, some will go to negative, some will go to positive. And then from there you distribute into the strips. For equivalent frame, we need to create equivalent frame. Now, what does it mean, the term equivalent frame? Because this is not a real frame. There is no real beam. It's a slab strip that we are trying to model as a beam. So the reality is that there is a slab which is very wide, maybe 8 meter wide beam, and columns are only supporting part of that, and we want to compress everything into one line so we can do the analysis as a beam. So that compression into one line requires some consideration, and that is why we call equivalent frame, not real frame. If this is just beam and column, that's a real frame. But if you're trying to convert a slab strip into a equivalent beam, then we have to do some reductions. So for lateral loads and gravity loads, we can do separate kind of analysis. So this is the problem. Why we have to create, why there's going to be a difference between the real frame and an equivalent frame. This is a real frame. So if you have a beam and a column, you apply a load here, whatever is the rotation here, same rotation will go to the column. There's only one location. So the column and beam are compatible, and they are going to show compatibility in terms of the deformations. So this can easily be represented by one line frame. If you have a slab and the same width of wall, same thing, doesn't matter, because each strip on the slab and column are the same, so we can divide it into small strips and we can analyze them as frames, because the deformation compatibility is 100%, is identical at every location along the way. This is a different problem now, because when the column is only here, the slab is going to deflect here and there, and also going to deflect here. So now the deflection at this location and deflection at this location will be very different, because first there is going to be deflection here, and then this deflection will start from the deflection point here, and then it will deflect more. So the transverse deflection will affect the deflection in various locations. So the deflections at the same section along this width will not be equal. Here they will be equal. Here they will be equal. So now that means there is going to be some leakage of stiffness. Some stiffness has leaked away into the torsional rotation here and transverse deformation there. Clear? So this must be taken into account while calculating the equivalent properties of the frame. So the column, relative stiffness of the column and the frame need to be adjusted. Basically, that's what we are saying. Here, they don't need to be adjusted because they are the same. So we can use the actual calculated stiffness of the column and actual calculated stiffness of the beam to do the analysis. Here we cannot do that because the stiffness of the slab and the column are now not compatible because column is only holding part of the slab, not the whole slab. So there is a leakage of stiffness. Do you understand this clearly? And that leakage is happening because of two factors. One is the twisting of this beam, because if this was completely rigid, then the deformation here will be transferred here and will transfer to the column. But this is not rigid. This is twisting and it's also deflecting. So we have two contributions to the reduced stiffness: the deflection, transverse deflection of the strip, and also the rotation of the strip, which is causing the middle this displacement to be more than it should be, more than here. So the average displacement will be different from what you get here. It will be more. So that means the effect of the column to restrain the stiffness has now reduced. So we need to reduce the stiffness of the column or adjust the column stiffness in such a way that these effects are taken into account. And this is the troublemaker in equivalent frame, making it complicated to use. Because to calculate that effective stiffness of the column is not that easy. Because you must take into account the torsional, rotational loss of the edge beam and also the transverse displacement of the edge beam. Without doing the calculations, in a finite element analysis, it won't be a problem because everything is modeled. You don't need to worry about this one. But in an equivalent frame, you need to worry about this one. Right? The other problem, this is problem number one. Second problem is that the properties of the slab along the length are not the same, unlike a beam. Beam has the same properties along the length. Here, we have different properties. Here, if we have a drop panel, different properties, and if we have a column capital, different stiffness, and within the column, different stiffness. So that means the same uniform stiffness of this section cannot be used because it's changing. Different elements are coming into the strip. And some are full width, some are not full width. So there could be a beam here, there could be a top panel there could be a column capital there. All of that will alter the stiffness of the beam. So we need to modify the stiffness of the beam, equivalent beam, because of the change of the section, and we need to modify the equivalent stiffness of the column because of the rotational loss of the deformation compatibility. So computer model needs to have many elements. One element from here to here, one element from here to here, one element from here to here, and one element from here to here. Each with its own properties at that section. So not one element, many elements must be created to create this equivalent frame. So that can handle the change of the stiffness along the span. Number one. Secondly, we need to modify the stiffness of the column above and below for torsional compatibility that we talked about. So two things need to be done. Include all the components in the beam modeling and modify the column equivalent stiffness. Once you do that, then you can run the analysis just like any other frame. Correct? So this is what we are talking about, that if this is the slab and there's a drop panel here, then the stiffness here will be bigger. Stiffness here within the column will be very large because columns cannot deform, and stiffness within this center line will be very small. So we need to make such adjustments in the modeling of this panel, right? And for the torsional component, we need to look at the torsional, the properties of this beam which is perpendicular to the column, not along the column, because that is the one which is providing that stiffness to us, both this way and torsional. So we look at the section of this beam, and based on the dimensions of columns and beams and everything, we calculate a property called KT, stiffness of the torsional element. I will show you. So basically, we do that two things. And KT or KEC is equivalent column stiffness is calculated by this formula, where KT is calculated, KC is calculated like this one, KT is calculated like this one, C is calculated like this one. And so basically the bunch of formulas that come in to calculate various stiffnesses of the cross beam. Right? So it's not rocket science, it's simple, just more work to be done. You just need to calculate these formulas are straight away given. The problem is calculating these C's and other things, it's a little bit of tedious, it's just too much of work. Too much of work actually in by hand. And that's why I told you when I started work long time ago, nobody wanted to do this extra work, so nobody designed flat slab, because why calculate KT when I can just put a beam there and forget about it, right? So all of this we need to understand and do that. Same thing again more clearly. And then after you do that, you create the model, you analyze it, right? Using any frame analysis program. And then you get these moments. Now, the effect of having changes in equivalent column stiffness, you can see that will affect the negative moment here, basically, in the strip. So if this is here, if the KEC or equivalent column stiffness is small, you get negative moment like this. If it is large, medium, you get moments like this. If it is very large, you get moments like this. So basically, this effect of the equivalent columns will affect the negative moment here, positive moment here, and negative moments a little bit. So the whole moment diagrams will be shifted up and down because of the end stiffness of the column. As you can imagine, if the columns are very rigid, they will attract a lot of many moment, negative. Positive moments will be reduced, but negative moments will be increased. But if they are flexible, it will be the other way around. So we need to be able to estimate it correctly, because if you don't, you will be in trouble. Suppose you estimate the stiffness incorrectly and you estimate it to be too small, right? Then the negative moment that you calculate here will be small, and which means your shear calculation of the column will also be wrong, because shear capacity or shear strength that you need to provide also includes moment transfer. And if you transfer the wrong moment, real moment is larger, you are in trouble, right? And your calculation for other moments will also be wrong. So you need to assess the right amount of stiffness to be able to calculate right amount of moments at various locations. These are total moments in the strip, right? Whole strip, including beam, drop panel, everybody. After you calculate that total moment, the next step is to distribute this amongst various components in the design strip. This is the easy way to understand what's going on in a slab system. Direct design method starts from here, which says WL squared by 8 is the total moment, sum of the negative and positive moment. As you know, it never changes. The reason I say WL squared by 8 is an amazing number, because this moment can never be changed no matter what the boundary condition, whatever it is, the total moment, sum of all moments must remain this. That's why this is a magic number, right? No matter what you do, determinate, indeterminate, whatever it is, ultimately this is the moment that you must get. The only thing that can happen is that some positive, negative moments will shift here and there, but sum of all moments will always be equal to this one, right? So in the direct design method, we calculate that directly. We say the total moment is equal to this one, and we just say, not correct. We say 35% is positive, 65% is negative. Because we have done this for simple boundary, we already defined that the panel is square, at least 3 panels, so we defined it clearly that for that particular condition, we can assume that the positive moment is going to be 35% of this one, negative moment is going to be 65% of that one. In the equivalent frame method, we don't do this like this one. In equivalent frame method, we calculate these moments through analysis, as I showed you earlier. Right? So we calculate the positive negative moment from the analysis. So we start from the equivalent frame method here. Direct design method, and after that, both the methods are the same. Then after we get the negative and positive moment in the frame, we say now part of that positive moment will go to column strip, part of that will go to middle strip. And part of the column strip will go to beam, part of that will go to slab. So everything is complete. It's like you get some fund and you have many people there and you distribute them according to their needs. Right? As simple as that. So same thing happens with negative moment, middle strip, column strip, B, slab and beam. If there is no beam, this becomes 0. If the beam is very big, this becomes 80%. Right? So it solves all of the problems in between, from no beam to very big beam. But if the beam is too big, this method doesn't apply anyway. If the beam stiffness is more than 5 times the slab thickness, because we saw the rules in the beginning, this method does not apply anyway. So then you calculate it based on the other way. So as long as the beam is not too big, up to 85% moment can go to the beam. 15% will still remain in the slab. Right? And so you can see, so this is a very nice, beautiful, neat way of designing things. And this range depends upon the relative stiffness of the slab and the beam. So you calculate that, and based on that there is a formula, you can distribute this way. If you are clear about this diagram, then my job is done. Anybody has any confusion about this diagram? The process or the understanding or the concept behind slab system design? Shear, now that was moment so far. We haven't talked about shear. Moment is easy. Shear is tricky. Very tricky. And shear is very problematic. Almost the slabs never fail by moment. They almost always fail in shear. Bending moment is a very forgiving thing, right? Shear is not forgiving. So don't underestimate the shear calculations. So shear, as you can imagine, is of two types in a slab system: one-way shear and two-way punching shear. So one-way shear means that the shear plane is here and part of the slab will break and fall down along this line, right? Second possibility is that the part of the slab will fall down and part of the slab will be in the column, which will remain, and the other part just breaks down and falls down. Punching shear. Most common problem in flat slab system is the punching shear failure. And as I told you, I have experienced once in my project already, right? And this is most common problem in failures is the punching shear. So you have to stay away from it completely. Right? Of course, this is relatively easy. It's like a beam shear. You calculate the shear based on the thickness and the width of this panel, and it's easy. And it's not that difficult. The problem comes with that, because we don't know what is the parameter of this pyramid to calculate the total punching shear capacity exactly. And the mechanism is very complicated because of the moment transfer also, right? So there are some basic assumptions. We have been talking about shear design in the last course also. We talked about punching shear. You remember that, right? We talked about punching shear. We need to calculate the capacity from concrete to carry the shear, and if that is not enough, we add reinforcement. But we try to avoid adding reinforcement for punching shear because it's very complicated to place in all directions. It's not that good. So we typically don't want to place punching shear reinforcement unless we have no choice. Strut and tie model can be used, if you remember. Shear strength, concrete strength, parameter thickness, shape and location. So these are the formulas to calculate the punching shear based on the concrete capacity alone. And you can see from here that this important thing is V naught. V naught is the length of the parameter of that cone that will be involved in punching shear, and that depends on the thickness itself, because that is the distance of that parameter from the column is related to the thickness of the slab. So it becomes a double equation in which thickness comes twice, once in V naught and once in thickness calculation, because you can see from here that this D also is here and D is also part of the parameter calculations. So, but this part is not the problem. The punching shear from gravity load or direct load is not a serious problem. It can be calculated easily. It's a problem, but not that serious. The problem comes from the moment transfer, the second part, which is because the shear is trying to, the moment is also trying, this is the column here, moment is trying to transfer here, and that is also producing additional shear, positive, negative, locally on the column itself, which is self-balancing, not coming from the load, but it is adding shear on one side and reducing shear on one side. We have talked about this last time. So you need to calculate how much to be transferred by bending moment, how much to be transferred by shear, and all of that. To prevent punching shear failure, we can do many things. These are some of them, right? Please remember them. We can provide large diameter bars at the bottom of the column so they can hang the whole thing if it fails, right? So we put the 4 bars, big diameter, calculate the diameter in such a way that if the slab fails, they can carry all the load by hanging the slab so that it doesn't fall down. It will be gone, but it won't fall down. So to prevent falling down, we can provide big bars at the bottom of the slab or over the column so that in case of failure, it supports the whole weight of the slab. That's very important, it's part of the code now. Provide proper reshoring of floor slab. Most failure occur during construction. Provide adequate punching strength. Use column capitals. Very most effective is column capitals. If you can use column capitals, it will solve the problem quickly. Avoid opening in the critical. Do not put openings in that zone. Corner column locations are often the most critical because of the moment transfer. Double moment transfer there. First of all, the bottling of the slab for detailed finite element is quite, I shouldn't say difficult, but it's time consuming both for you and for computer, because you create a lot of mesh. You have many details, openings, inclined columns, staircases, cantilevers, shifting columns, many complications in a real slab. So if you want to do the detailed analysis in finite element, all of those things need to be modeled, and that creates just more work, but it can be done. The programs can help you to do auto meshing. Automatically they can, for example, if I give you this example here, forget about this one. This is basically saying what the program will do to do the auto meshing of the line object. Okay, let me show you a little bit, just the concept. The concept is, if you have a slab like this one, and you have 4 columns, and you have these girders. Now, if you want to analyze this in finite element, this problem becomes quite a tricky one. Why? Especially automatic meshing. Why? Because we must mesh all of these in such a way that they are all interconnected. There are sufficient elements there, and the loads are transferred from one to the other correctly. That means we must mesh this portion, we must mesh this girder, so these are connected here, we must mesh, and we must mesh the connectivity of these beams, and also the load transfer from one beam to the other, from this to the other. So if the meshing is not complete, load will leak. Some load will not be transferred to the supporting beams and will not go to the columns and so on. So automatic meshing needs to take care of all of those things, and I'll show you an example here. So suppose this is your slab panel, just resting on 4 columns and 4 beams. This is just like this table. So what is that the program needs to do before it can mesh it? It needs to first of all extend the, and this is what you should also do manually if you want to do this one, right? This is also an understanding of how to work. First of all, you must extend these, even if there are no beams here, you need to extend them to the edge, the lines, right? Then after that, you divide it into panels like this. And then after that, you subdivide these into further sub-elements to capture the deformation properly. If you just do this one, it will not work. Because to capture the deformation in a slab panel, you must have at least 4 by 4 mesh, irrespective of the size of the panel. Some people say the mesh size should be 1 meter by 1 meter. It makes no sense at all. It has nothing to do with the real dimension of the slab or real dimension of the object. It is to do with the deformed deformation pattern and how many elements are required to capture that deformation. So if you deform something, you need at least 4 elements to capture the deformation. 4 this way, 4 this way. So each panel then must have about 16 or 25 mesh elements in between. So you tick, 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 and then you get the mesh, right? So if this is the case, if there are no beams, you still need to introduce artificial beams on the column lines, and you still need to extend them, and they still need to come up with the same mesh. If you just try to mesh it without this one, it just won't work, because you need to have meshing going everywhere, right? And then after that, you then need to subdivide it further to get to capture the deformation. This will only ensure basic load transfer. It will not ensure the deformation, deflection, or bending moments in the slab. For that, you need to submesh it again. And these are the parameters that control in ETABS, how the program will do all of that. And this is subdivide the objects into sub-elements of that size. So after that, it will do that once again, right? So the results will be something like this. If this is the real slab, which is quite common, you just draw the outline as shown by dotted line here, and you draw all of that, all of that, all of that, and that's it. One object. You draw a slab line. And then you ask the program to do auto meshing for this one. If you do manually, it can take you many, many hours to do this. If you ask the program to do it, it will do this meshing. So it will create thousands of elements from that automatically by using the rules that I just showed you before. So it will extend, put here, subdivide, subdivide, subdivide everywhere, and this one should work. So you can imagine that to analyze a slab by finite element, you need thousands of elements. And if you have many floors, multiplied by that, it becomes a very big model. It takes a lot of time to run. That's why for slab design, we normally use another program which goes slab by slab, safe. And for overall analysis, we use a mesh which is not so fine, because we are not worried about the local deformation, we are only worried about the load transfer. So for load transfer, this level of mesh will be okay. But for calculation of the slab deflections and moments and design, you need this one, right? Auto load transfer, as I mentioned to you, the program will try to transfer load from one element to the other. But if you use shell element, you don't need to worry about this. Everything will be correctly done. This is only a worry if you use membrane to model the slab, which you should not use. But people had no option than to use that earlier because shortage of memory of the computers and speed. But these days, most engineers would mesh the slab by using shell. So that this problem does not happen except for steel structures, where you may still use this one. So here, if it's a steel structure, then it's a deck. So you can specify that my load will be transferred only in this direction. So the load will be transferred like this. You mark the direction, and then load transfer happens in this direction, and then the load comes out to be exactly W by 2, W by 2. So you can still force the program to calculate the load based on geometry distribution in steel structures, and the program can help you to do that through this process. So you can put a deck and you can say, I want to transfer the load like this. The program will do the calculation just like as if you will do hand calculations based on geometry. And then many other cases are specified here. But I would never use geometry based load transfer for a complicated slab like this. Use shell elements, because this is not reliable. It's not correct. But yes, if you have to, you can. Even for openings, you can do some manual. The reason all of this was given at some time that this was essential to finish the project. Alright, so that completes the gravity load analysis for buildings. Any questions?